So in this video, we're going to be looking at the structure, the properties, and the general reactions of our alcohols. Now, starting off, alcohols, they're going to be polar molecules. The reason why is because we're going to have an overall dipole. Now, this OH group over here, that's going to be, of course, the general polar part of the molecule. We know we've got oxygen. Oxygen is going to have a higher electronegativity. It's going to be more electronegative compared to the hydrogen and the actual carbon in a molecule of alcohol. In this case, I'm dealing with methanol, and the oxygen is going to be more electronegative. It's going to have a greater ability to attract electrons towards itself compared to that of hydrogen and compared to that of carbon as well. Now, this gives rise to many different properties. The first one that we're going to look at is going to be the boiling and melting points. Now, when we look at, let's say, our alcohol, which is going to be in this case ethanol, and we were to compare that to something like an alkane, like ethane, we know ethane has induced dipole-dipole interactions only. Alcohols, they're going to have hydrogen bonding between the molecules. We know the hydrogen bonding is going to require more energy to overcome because it's going to be stronger. So in that case, our alcohols of the same carbon chain length compared to, of course, our alkanes, they're going to have a greater boiling point overall. Now, we can also represent this using a hydrogen bonding diagram. You can see over here, I've got my alcohol molecule ethanol. I've got my partially positive carbon, partially negative oxygen, and a partially positive hydrogen here as well. And we know the lone pair on the partially negative oxygen is going to be attracted to, from this alcohol, to the OH hydrogen over here. Not just any hydrogen, but the OH hydrogen that's going to be partially positive as well. Of course, we've got a labeled hydrogen bonding diagram. To make things easier, just remember that it's easier to actually flip the ethanol molecule rather than drawing it out and trying to get to matching displayed formula. Now, another property in which impacts the actual boiling and melting points of our alcohols is going to be the number of OH groups. The more OH groups you have, the higher the boiling and melting point is going to be. The reason why is because they can actually form more hydrogen bonds between molecules, which requires more energy to overcome. So I've got ethanol over here. I've also got ethane 1,2-diol. Now, in terms of these two, I know ethane 1,2-diol is going to have a higher melting and boiling point. Now, the reason why is, of course, ethane 1,2-diol, that's going to form more hydrogen bonding between the actual molecules compared to ethanol, which just forms, of course, half the amount of hydrogen bonding between the molecules itself. So moving on to our next property, we can look at the solubility of our alcohols. Now, short chain alcohols, they're going to be very soluble in water, and the reason why is because your alcohol, like ethanol, let's say, is going to form hydrogen bonds with water molecules. You can see we've got another diagram over here. Again, same thing. I've got ethanol, partially negative oxygen, partially positive carbon and hydrogen, and we know the partially positive hydrogen is going to attract the lone pair. It's going to form a hydrogen bond to the lone pair on the partially negative oxygen atom. Of course, it can be flipped the other way around, so it could be between this oxygen over here and this hydrogen over here itself. Again, we do need a label, but just remember it's going to be between ethanol and water when we're trying to show a hydrogen bonding diagram for solubility. Now, when it comes to the solubility of our alcohols, we need to look at the carbon chain length. The longer the actual carbon chain, the less soluble our alcohol is going to be. The reason why is because we end up with stronger induced dipole-dipole interactions between the actual molecules, and they break up the hydrogen bonding between the molecules as well. So we look at it, right? I've got a bunch of different alcohols at the bottom over here. Heptan 1-ol is going to be a lot less soluble compared to something like propan 1-ol. The reason why is because, of course, of that long carbon chain. This non-polar group over here is going to be larger, and the induced dipole-dipole interactions between the molecules is going to break up this hydrogen bonding. Compared to that, of course, propan 1-ol, it's got 3 carbon atoms there. It's got much less induced dipole-dipole interactions. Now, when we look at the number of OH groups, the more OH groups we actually have, the more soluble our alcohol is going to be in water. The reason why is, again, we're forming more hydrogen bonds with the water molecules. Look over here, I've got propan 1-ol versus propane 1,3-diol. In the case on the left, I've got 1 OH. On the case on the right, I've got 2 OHs. The more alcohol groups we have, the more OH groups we have, the more hydrogen bonding we form between our actual molecule and the water molecules. And so propane 1,3-diol is going to be much more soluble compared to that of propan 1-ol. Now, moving on, if we were to look at the reactions of alcohols, there's a bunch that you need to be aware of. A lot of them that you'll deal with in module 4, but then some of them you'll deal with in module 6. The first one is they can react in redox reactions to form alkoxide salts. The second one is another one we're covering in this this video, where you can end up with combustion reactions to form carbon dioxide and water. And then another two for another video is going to be the substitution to form haloalkanes. So you've come across alkali hydrolysis, this is going backwards. And then we've also got dehydration, which is the opposite of hydration reactions for our alkenes. Another video, we've got oxidation to form our aldehydes, ketones and carboxylic acids, and that depends on what type of alcohol you've got, be it primary, secondary or even tertiary. And then one for module 6 is going to be the esterification reactions to form esters as well. Now, one important thing to note about our alcohols is unlike carboxylic acids, the hydrogen on there, and unlike phenol as well, the hydrogen on there is going to be, of course, neutral. It's not going to be acidic, and so we know, right, they actually make neutral solutions. Their pH is going to be equal to 7. Now, if I were to look at, right, our first reaction, our redox reaction, we can actually show this because it's very similar to how carboxylic acids react with metals in redox reactions, not neutralization. Our alcohols react with metals to form alkoxide salts, and alkoxide is basically just when you've got an alcohol, right, you've removed the actual hydrogen from there and you're left with a negative charge, followed by, of course, a counter ion, which could be any metal plus ion itself. So yeah, our observations are just the same. We see our solid dissolving, and then we see fizzing from the hydrogen gas produced as well. An example here, we're reacting sodium with ethanol to form sodium ethoxide, and of course there's our equation over there as well. Now, in terms of this, we can see, of course, it's a redox reaction because the actual hydrogen is going from +1 oxidation state to a 0 oxidation state here. Sodium goes from 0 to a +1 oxidation state over there. Remember, your ethoxide actual ion is going to look like this. You've got ethoxide there and you've got sodium plus over here. The bonding over here is going to be ionic because you've got the strong electrostatic attraction between oppositely charged ions. We know it's a redox reaction because the hydrogen is reduced from a +1 to a 0 oxidation state, or in terms of gaining electrons, it's gained 1 electron. Sodium is going to be oxidized from 0 to +1 oxidation state. We know it does this in terms of electrons by losing 1 electron. So we know, of course, we've got a redox reaction here. Now, in terms of combustion reactions, that's our second type of reactions. Alcohols, they can be oxidized by combustion like most other organic compounds, and they're actually going to be very good fuels because they've got very high enthalpies of combustion. They produce a lot of energy per mole of alcohol we actually burn. Now, if you were to look at this, right, ethanol versus ethane, we actually prefer our alcohols because they burn more efficiently, because they actually have an internal supply of oxygen, and that's going to be in the form of an OH group, and that's why we actually add it to petrol mixtures of octane. We add some ethanol in there to prevent any incomplete combustion from happening and taking place to produce things like carbon monoxide. Now, look at ethane versus ethanol. Ethane is going to be C2H6, and if we were to form a balanced equation, we react it with oxygen, we end up forming 2 lots of carbon dioxide, we form 3 lots of water. In total, we've got 4 lots of oxygen, added to 3, that's 7. That's going to be 7 over 2, there's 3.5 lots of oxygen there. Now compare that to ethanol, which is going to be C2H6, and then it's going to be O, or you could have said C2H5OH, either one's going to be fine. But yeah, you react these with oxygen, right? In this case, you produce the same amount of carbon dioxide, the same amount of water as well, but the only difference is you've got 4 oxygens there, 3 oxygens there, that's 7 lots of oxygens to make up for. You've got an internal source over here, so you actually need less oxygen, 3 lots of oxygen, 3 lots of O2 for complete combustion to take place. Now, that's why we actually add ethanol to our petrol mixtures, so we're preventing the amount of incomplete combustion from taking place. We're preventing and reducing the amount of carbon monoxide, carbon particulates being formed, and promoting more complete combustion because we've got that internal source of oxygen here. Now, moving on, I've got a task for you to try. Feel free to pause the video, have a go, resume once you're ready to go over the answers. So you're looking at this first question. We're asked to write balanced equations for the complete combustion of pentan-1-ol. So pentan-1-ol, we know, of course, we can draw it out and we can end up with something that looks like this over here. Count our number of carbon atoms, count our number of hydrogen atoms, and then the oxygen as well. Or what we can do is remember the general formula, which is CnH2n plus 2, and then O, or you can remember it like this, which is CnH2n plus 1 OH. Now, in this case, I'm going to go with the one on the right. So, of course, I've got CnH2n plus 1 OH. So, I've got C5, and then it's going to be H11OH. Again, it reacts with oxygen. What do we produce? Well, in this case, I'm going to produce carbon dioxide, and then I'm also going to end up producing water as well. How many carbon dioxides? It's 5. Remember to balance it using the Cho method. So carbons first, then hydrogen, which in this case I've got 12 on the left, so I've got 6 on the right over here. Now we're about balancing the amount of oxygen, where I've got 6 oxygens there. 2 times 5, that's 10, that's 16 in total. I've got 1 in there, so remember I'm going to have to make up for 15. Don't forget the internal source of oxygen. 15 divided by 2, I end up with 7.5 in total. There's the oxygens balanced. What about the next one? Right, we've got 2-methyl propan 2-ol over here. So I've actually got my alcohol at this 2 position, the methyl at that 2 position. You can actually just work out each carbon atom, how many hydrogen atoms and oxygen atoms, but I'm just going to look at the general formula again. I've got 4 carbon atoms altogether, so I know using my general formula it's going to be C4 and then H2N plus 1, so it's going to be H9OH. So there's butanol technically, and then I'm going to react that with oxygen again. I'm going to end up producing carbon dioxide and then water, and then what we end up with is balancing the carbons again. So I need 4 lots of carbon dioxides. Hydrogens, I'm going to have 5 lots of waters, because that's going to make, of course, 2 times 5, that makes 10 on the left. And then the oxygens, well, I've got 2 times 4, that's 8. 8 added to 5, that's going to be 13. 13 minus 1 is going to be 12. 12 divided by 2 gives me 6 oxygen molecules. And there's those 2 questions done and balanced. Look at the next question. Using structural formula, we need to write an equation for the reaction between propan 1-ol and sodium. Well, propan 1-ol is going to look like this, where we've got CH3, CH2, and then it's going to be CH2OH. That will react with, of course, sodium. We end up producing, in this case, CH3, CH2, CH2, ONA, and then we end up with hydrogen gas. But remember to balance this, you can just put a 0.5 there, or you can double everything else. There's that equation done. The observations is that you see fizzing and the solid dissolves. What about the equation using skeletal formula this time for the reaction between butan 2-ol and potassium? Well, butan 2-ol is going to look like this, where I've got an alcohol at the 2 position. That reacts with potassium. What do we end up producing? Well, I'm going to end up with, of course, my alkoxide, which looks like this, bonded to, of course, a sodium. To emphasize the ionic bond, I put a plus and a negative there. So I end up with this structure over here, and then I end up with hydrogen as well. Make it balance, 0.5, and there's that balance too.